Today I'm going to continue the discussion of basic chemistry, but today looking at chemical bonds and chemical reactions. So we should have a good foundation now in atomic structure, electron distribution, and predicting whether atoms are likely to react with one another or not. So one of the terms that we use when we have interactions or bonding between two or more atoms is the term compound. So a compound is two or more atoms of different elements chemically bonded together. And you should be able to recognize compounds. For example, sodium chloride, two different elements, sodium and chlorine. This is the molecule glucose, but we can see that there's carbon, hydrogen, and oxygen. So both sodium chloride and glucose are both compounds. Carbon dioxide, again, we see carbon and oxygen. That's another example of a compound. Now, O2 is a molecule, but it's not a compound because here we just have two atoms of the same element. All right. So next I want to look at chemical bonds. Chemical bonds are the result of atoms either sharing or transferring electrons. So when there's a transfer of electrons, that's known as an ionic bond. And what I mean by a transfer is that's a giveaway, where one atom is careless with its atoms and another atom is selfish, and it will take those electrons away. And so again, it would be like a transfer of money. If I transferred money from my bank account to your account, that's not my money anymore. I've lost that money. You're not likely to give it back to me. And that's not going to happen, by the way. Now, a covalent bond would be a sharing of electrons between two or more atoms. So here, electrons are going back and forth between two different atoms. And we'll look at that, both of those examples here in a few minutes. All right, so let's first look at an ionic bond. And this would be an example of an ionic bond between a sodium atom and a chlorine atom. Now again, you should have a good foundation in the structure of the atom. So if we look at sodium, sodium is element number 11. It has a mass of 23, so you should at this point know that it has 11 protons and 12 neutrons. And we would again start with the assumption that there are an equal number of protons and electrons. So 2 electrons would go into the first orbital, that's the maximum there, the next 8 into the second shell or orbital, and a single electron in the outermost shell. So here then, the atom potentially could either lose that electron to have a full shell underneath, or it could gain 7 more to fill a subshell. And I think intuitively you probably realize that it would be easier to lose 1 electron than gain 7 electrons. Now, if we look at chlorine, element number 17, mass 35, so 17 protons, 18 neutrons, we would again work with the assumption initially that there are 17 electrons as well. So 2 of those electrons into the first shell, that's the max it will hold, 8 more into the second shell, and then we would have 7 left over spilling into the first subshell of the third shell. And you may recall that that holds a maximum of 8 electrons. So to fill this shell then, chlorine could either pick up 1 electron to fill the subshell, or it could try to lose its 7 electrons. And again, it's really easier for it to pick up an electron rather than try to give away 7 electrons. So in our ionic bond here, this is the before picture. Sodium is a neutral atom, chlorine is a neutral atom, 1 electron in the outermost shell, 7 electrons in the outermost shell. And I think then you can see that to make everybody happy, so keep in mind that what really drives chemical bonds is that atoms want to have full shells or subshells. This is not full, this is not full. How can they make each other happy? Well, again, hopefully you can see that if you transfer 1 electron from sodium to chlorine, that will make the difference. So the after picture then would look like this. Because sodium has given away its electron, that shell no longer exists, so its second shell is full. Chlorine has picked up an electron, and that subshell is full. So they are quote-unquote happy. That makes them happy. However, what you may also notice now is that our charges are no longer in balance. So we have 11 positively charged protons in the nucleus, only 10 negatively charged electrons in the orbitals. So that means then that sodium has a net charge of +1. Chlorine, on the other hand, now has 17 positively charged particles in the nucleus, 18 negatively charged electrons in the orbitals or shells, so it takes on a charge of -1. So, as you may know, opposites attract, and so it is this electromagnetic attraction then that holds the sodium and the chlorine together. So this is our after picture. Okay, also we can do a little animation that will show this as well. So again, we have our sodium, we have our chlorine, 1 electron in the outermost shell, 7 electrons in the outermost shell, and we're looking for these to combine. So there's the transfer of the electron. They take on charges. That's what holds them together. Now, positively charged particles are called cations. Negatively charged particles are known as anions. And the term ion refers to any charged particle. Now, in this case, sodium chloride, as we can see, they have different charges, and so that's what will hold them together. And actually, this is common table salt. So our common table salt is sodium chloride. You can see that actually it normally forms a solid crystal-like structure. Another example of an ionic bond that involves more than 2 atoms would be magnesium fluoride. So in this case, we're going to have 1 magnesium atom and 2 fluorines. So that's what that little subscript here is telling us. There will be 2 fluorine atoms. So again, in our before picture, again, fluorine is atomic number 9, mass of 19. And so we would work on the assumption that there are 9 electrons as well. So 2 electrons in the first shell, 7 would go in the second shell. The same would be true of our second fluorine over here. And then magnesium, element number 12, atomic mass 24, so 12 protons, 12 neutrons. We would start with the assumption that there are also 12 electrons, the first 2 in the first shell, next 8 in the second shell, 2 left over in the outermost shell. So again, these are both reactive atoms. Fluorines have 7 electrons in the outermost shell, and if they could pick up 1, that would fill that shell. Magnesium, on the other hand, has 2 electrons in its outermost shell. This being a subshell, it would need to pick up 6 electrons or lose the 2 that it has. And again, I think intuitively you probably can see that it would be easier to lose 2 than gain 6. So again, if we look at our after picture here, that's exactly what's going to happen. Magnesium would give 1 electron to each of the 2 fluorines. So each fluorine then would have 9 protons and 10 electrons now. So each fluorine would take on a negative charge. So there would be ions, negatively charged ions or anions. Magnesium, having lost 2 electrons, now has 12 positively charged particles, only 10 negatively charged particles. It takes on a charge of +2. So these particles of different charge then are held together by the electromagnetic attraction. And I do want you to notice in both the previous example and this example, if we look at the net charge, even though there's been a transfer of electrons, the overall charge is still neutral. So magnesium is +2, but there are 2 negative charges to offset that. So the overall compound is neutral. Now, ionic bonds have certain characteristics. One of these being that they tend to form between metals and metalloids and nonmetals. And so when you look at the periodic table, most periodic tables will have a dark line here, and that separates the metals and metalloids from the nonmetals. So metals and metalloids tend to lose electrons. The nonmetals tend to gain electrons. So these different groups tend to form ionic bonds with one another. This group also would go into that metal or metalloid composition. They tend to form between atoms with very different electronegativities, and I'll talk more about that later. They tend to form hard, brittle compounds with high melting points. And again, table salt would be an example of that. And then most readily dissolve in water, forming free ions or electrolytes in that water. And so again, if we look at this diagram, you can see that actually what happens is that water molecules will wedge themselves between the sodium and the chlorines so that the compound actually separates in the water when it dissolves in the water. Now, covalent bonds, instead of a transfer of electrons, involves a sharing of electrons. And so there are 2 types of covalent bonds, but I'll talk about that more a little bit later, polar and nonpolar covalence. So covalent bonds, again, involve a sharing of electrons. So if we look at the before picture here, and an example of a molecule that forms a covalent bond would be water. And so we're going to be looking at 2 hydrogens and a single oxygen. So here's our oxygen, and here are the 2 hydrogens in our before picture. And oxygen, as you can see, has an atomic number of 8, mass of 16, so 8 protons, 8 neutrons. So the first 2 electrons go into the first shell, and then the remaining 6 go into the second shell. And when we draw out these covalent bonds, we normally show the specific electrons, and then you will need to draw a key showing the electrons of each element. Hydrogens we've seen before, so 1 proton, atomic number of 1 proton, and 0 neutrons in the nucleus. Since there's 1 proton, again, we would assume a single electron, so 1 electron in the only orbital. And then these will interact in a way that they will share electrons. And so this is how we visually represent that sharing. And so what actually is happening here then is that hydrogen will not only have an electron that will orbit its own nucleus, but it will share that electron with the oxygen, and it will also orbit the oxygen. This hydrogen will be doing the same thing. Its electron will orbit the hydrogen, but it will also orbit the oxygen. So oxygen has at its disposal then not only its own 6 electrons, but 1 each from the 2 hydrogens. So that gives it a total of 8 electrons at its disposal, and so it behaves then in a more stable way. It thinks that it has full shells. Each hydrogen, of course, would not only be using its own electron, but it would also be borrowing an electron occasionally from oxygen. So these electrons from oxygen would not only orbit the oxygen nucleus, but occasionally the hydrogens. So each hydrogen then would have 2 electrons at its disposal, filling its shell. So these covalent bonds then share electrons, or atoms that covalently bond will share electrons in a way that fills outer shells. Another example would be methane. So methane is CH4, 1 carbon, 4 hydrogens. So as we look at carbon then, atomic number 6, mass number of 12, so 6 protons, we would assume 6 electrons, so 2 electrons in the first shell, 4 in the second shell. So it will share with hydrogens, and so we again show overlapping orbitals. And so the carbon then will share 1 of its electrons, not only with itself, but also with a hydrogen. So each of its 4 electrons will orbit itself in each hydrogen. And each hydrogen will not only have an electron that orbits its own nucleus, but it will share with the carbon. So carbon then effectively has 8 electrons in its outermost orbital, at least electrons at its disposal. Each hydrogen has 2 electrons filling its shell available to it. So again, they are under the illusion at least that they have full outer shells. And then last but not least, another example that's not a compound, O2. This is how we normally find oxygen in the atmosphere. Here's our before picture, here's our after picture. Now the difference here though is that instead of each oxygen sharing 1 electron with one another, they're actually sharing 2 electrons with one another. So that's what we call a double bond. So when atoms are sharing more than 1 electron with another atom, if they're sharing 2 electrons, we refer to that as a double covalent bond. Now, typically I'll be representing covalent bonds with just lines. It is important to know how to draw them and understand what's going on, but whenever you see a line like this, what that's telling you is that these are atoms that are sharing 1 electron with one another. If you see a double line, that's a so-called double covalent bond. It means that they're sharing 2 electrons with each other. If you saw 3 lines, that would be a triple bond, 3 electrons each with one another. Okay, so looking at characteristics of covalent bonds then, they tend to form between nonmetals with similar or moderately different electronegativities, and I'll be getting back to that in a few minutes. And so again, they tend to form between nonmetals, and hydrogen usually is typically included as a nonmetal. Sharing may be unequal, resulting in polar molecules, and we'll be discussing that shortly. Covalent bonds are stronger chemical bonds than ionic bonds. And when soluble in water, covalent molecules do not tend to dissociate from one another. The atoms do not tend to dissociate from one another the way that we saw in the ionically bonded compound. So this is representing then this blue molecule is representing a covalently bonded molecule, and you can see that it stays together and it's surrounded by these water molecules, which are the red and white ones. Now, getting back to covalent bonds then, what I mentioned earlier is that the sharing is not always equal. So an example of an unequal sharing of electrons occurs with the water molecule. And when there's an unequal sharing of electrons, this is known as a polar covalent bond. And these are polar covalent molecules. So that at any given moment in time, oxygen is hoarding the electrons. Most of the electrons will be in the oxygen end of the molecule. And so the oxygen end of the molecule takes on a slightly negative charge. The hydrogen end takes on a slightly positive charge. So this is like the poles of a magnet, negative and positive regions. And so this is known as a polar molecule. So again, an uneven sharing of electrons. Now, what happens then, and here's another example, is ammonia. So ammonia, again, is slightly negative at the nitrogen end and slightly positive at its hydrogen ends. Now, what this causes then are interactions between adjacent molecules. And again, if you have a slightly positive region of a polar molecule, it can interact with the slightly negative region of another polar molecule. And so when this involves hydrogen, we refer to these as hydrogen bonds. So these weak electromagnetic interactions between different molecules we call a hydrogen bond. And it's recently been discovered that that actually is a very, very weak covalent bond. So actually sometimes electrons may even go between molecules in these kind of situations. So an example of a nonpolar covalent bond would be methane. In this kind of situation, the electrons are evenly distributed at any given moment in time. There's no distinct positive or negative regions. Now, electronegativity is a measure of an atom's affinity for electrons, its capacity to attract and hold electrons. You can think of it as the selfishness of a particular atom. The more strongly it holds an electron, the greater its electronegativity. So, electronegativity then has an influence on bonds. If atoms have similar electronegativities, that forms a nonpolar covalent bond. If there's a moderate difference in the electronegativities, or how strongly two different atoms will hold electrons, that's known as a polar covalent bond. Or it will form a polar covalent bond. And then if there's a very large difference between the electronegativities, what will happen is a transfer of electrons, and that's an ionic bond. So earlier, we filmed a demonstration to show the differences between the different types of bonds and the influence of electronegativities, and so I'd like you to take a look at that now. Kayla and I are going to demonstrate the difference between a polar covalent bond, nonpolar covalent bond, and ionic bond, and the role of electronegativities in what type of bond will form. And so the analogy here is that we're going to be like two children playing. And so we're going to be, sharing tennis balls with one another, and also representing atoms sharing electrons. So initially, what we're going to start off with is we're going to say that we have similar temperaments. So let's say that we're both very sharing. And this, again, in terms of bonding, would mean that we have similar electronegativities. So if we have similar temperaments, similar electronegativities, and keeping in mind that electronegativity is kind of the selfishness of an atom. So neither one of us is particularly selfish related to electrons, and let's see what would happen then. So we're going to share. And you'll notice that we're sharing nicely. So that if at any given time we were to stop, we would each have an equal number of tennis balls, in this case an equal number of electrons. So there's no net charge to our molecule. So this would be what you would find in a nonpolar covalent bond. So we're sharing, that makes it covalent. There's no region of positive or negative, that makes it nonpolar. So again, that occurs when you have similar atomic temperaments or similar electronegativities. Okay, now let's see what would happen if I'm a little more selfish. What if I have a slightly stronger electronegativity compared to Kayla? So that means then I have to think about it a little bit, but I'll still share. So it's still a covalent bond because we are sharing still. But if you were to stop time at any given moment, I'm more likely to have the electrons, or I'm likely to have more electrons than her. That will make my end of the molecule slightly negative compared to hers. So this would be a polar covalent bond. Okay, last but not least, what if I'm a much more selfish kid than her? So instead of a moderate difference in temperaments or electronegativities, what if there's a big difference? She has low electronegativity, I have high, or she's not very selfish, I'm very selfish. So now when we try to play, I just take it and I keep the ball. Or in this case, I'm keeping the electrons. So now it's not a sharing anymore, it's a transfer. I'm stealing it, I'm taking it. So now I permanently take on a negative charge, I'm an anion. She now has permanently a positive charge since she's lost an electron, so she's a cation, and that electromagnetic attraction is what keeps us together. So that then is the difference between a nonpolar covalent, a polar covalent, and an ionic bond. Now, another factor that will influence bonding is quote-unquote compatibility. And that has to do with how many electrons an atom needs to fill a shell, or how many electrons it needs to get rid of to fill a shell, or sharing of electrons in a way that will fill shells. So to determine this, we look at the outermost shell, the so-called valence shell, and we look at whether it's full. If it's not full, what does it need to fill the shell? So electrons being transferred or accepted must be equal between different atoms, and this is what I mean by compatibility. So again, if we go to the periodic table, we can kind of illustrate this. If we look at all the members of this group, 1A, they all have one electron in their outermost shell. And they basically want to get rid of that electron to fill so they'd have a full shell underneath. If you compare that to group 7A, these all have 7 electrons in their outermost shell, and they're looking to gain an electron. So any member of group 1A will form a bond with any group member of 7A, because these need one electron and these want to dispose of one electron. So that's what I mean by compatibility. If we look at the next group, 2A, these all have 2 electrons in their outermost shell. So they're trying to dump those 2 electrons. And then if we go over to 6A, these are looking for 2 electrons. So any member of 2A is likely to bond with 6A. We could also look at 2A, trying to get rid of 2 electrons. They could also bond with any 2 atoms from this column. So ultimately then the number of electrons being disposed of have to equal the number of electrons being accepted. Okay, now, chemical bonds can be broken and reestablished. And when that happens, that leads to a chemical reaction. And so we use what are known as chemical equations to represent chemical reactions. And this is an example of a chemical equation. So we have 1 molecule of glucose composed of 6 carbons, 12 hydrogens, and 6 oxygens. And if we combine that with 6 molecules of oxygen, so again, O2 is a molecule composed of 2 oxygens, the coefficient in front is telling us we have 6 of those. So if we were to combine those, we will end up then with 6 carbon dioxides composed of 1 carbon and 2 oxygens. So the subscripts tell us how many of each atom there are. If there's no subscript, it means there's 1. So there's 1 carbon here, 2 oxygens. And 6 waters composed of 2 hydrogens and 1 oxygen. Now, on the left side of the arrow, we refer to those as reactants. On the right side, we call those the products. And the arrow is a yield sign indicating that there has been a reaction. And essentially what a chemical reaction is a rearrangement. Now, I won't be asking you to balance these equations, but you do need to recognize that they are written properly. And if it is written properly, the first, or the law of conservation of matter states that there can be no creation or destruction of matter. So we should start and end with not only the same elements, but the same number of atoms of each element. So if we look at the reactant side then, there are 6 carbons on the reactant side. So 6 carbons here. There's a total of 12 hydrogens. So 12 hydrogens. And then oxygen, there are 18. So we actually have 2 times 6 is 12, plus the 6 in the glucose is a total of 18 oxygens. Now, if this is written properly, I should have the same elements and the same number of each on the other side. So again, here I have 6 carbons because there are 6 carbon dioxides. Again, we have 12 hydrogens. H2 times 6 is 12 hydrogens. And 18 oxygens, so we have O2, but 6 of those, plus 6 oxygens that are in the water, for a total of 18 oxygens. So again, this is one that was actually written correctly. Now, one other thing I want to mention is that when we look at equations, we're not actually talking about numbers of atoms or numbers of molecules. The coefficients in front actually represent a number that's known as a mole. And so this term mole actually represents a number. So the number is a really big number, 6.02 times 10 to the 23rd items. And so the word mole then is similar to other words that we know, like the word dozen represents 12 items. A baker's dozen represents 13 items. A mole represents 6.02 times 10 to the 23rd items. So that's an awful lot of items. So if I go back to our reactants here, this really isn't describing a single molecule. We're talking about 1 mole of molecules. And this isn't 6 oxygen molecules, it's actually 6 moles of oxygen molecules, and 6 moles of carbon dioxide, and 6 moles of water. So the mole then is the standard unit of chemistry. And I will normally be talking about these as if we're talking about individual atoms and molecules, but again, technically we're talking about moles of these. Okay, the last thing I want to mention is that some reactions are reversible. So for example, here we have H2CO3, which can give up and yield one of its hydrogens when it's in water. But they can also recombine and go in the opposite direction. So some reactions that occur in nature can go in either direction, and what influences that really is typically on the reactant side. If you were to remove hydrogens from here, or if you remove these bicarbonate ions, that would make this more likely to dissociate. But that's something that we're going to be discussing in a future module. So in summary then, really we are complex solutions, and there are a number of chemical reactions ongoing in these solutions within our cells that are responsible for our life. And if something interferes with those chemical reactions, we stop living. The other thing to keep in mind is that really chemical reactions are not random. I hope you can see now that compatibility and electronegativity determines what kind of chemical reactions will occur. And the same laws of physics that apply to the non-living world apply to us. So until the next time.